Hello, everyone. My name is Roberto, and today I'll be talking a bit about how we use Temporal at Retool, kind of a user story of our journey, kind of adopting Temporal, what our motivating use cases were for doing so. We have this product called Retool Workflows. That's the team I work on, and originally this was built not using Temporal. We were really having lots of challenges with how we were running these Retool workflows. We decided to look at for other changes, other software that we could use, and we settled on Temporal. Kind of going to go through the first year of us launching this software, kind of from building the proof of concept to all of just the V0 latency and issues we ran into just hitting platform limits. And then once we had that V0 going to production, what actually leveraging Temporal's power has given us the ability to do, and basically everything we have been able to add on to it and the trade-offs we've had to think through. And so before I start, I'm going to talk about what a Retool workflow even is. If you saw the title, orchestrating complex customer-defined DAGs is not super intuitive, not very descriptive in its own. And so just to give you a bit of an overview of what a workflow is, this is kind of what our front end looks like. The basic primitive we give customers are these blocks. These blocks can include any type of arbitrary code. So you can have JavaScript, Python, you can make network requests, Postgres queries, gRPC requests, etc. You can kind of add these building blocks as you want. And the main feature we provide to you is this graph structure. We enforce that there aren't any cycles in the graph. And we also make all data from each block available to its downstream blocks. So you can kind of think of this as a flow of data way of thinking about what you run. Pretty similar to what Workflows is. We had kind of started doing this beforehand and kind of making it easier to do in the UI. Something else I want to kind of just draw your attention to kind of help define the problems we're trying to solve. We have this kind of root node in our graph of Temporal. Essentially, we have a start trigger. We always know that every time you want to run your code, this is where we begin. You can either set it to run as a cron string, so you could be run this graph once every minute, once every hour, or you can actually run it as a webhook. And so you'll trigger an execution every time you hit the URL, and you can even just pass in different body parameters, and they'll be used as inputs. And so this is what the front end looks like. We have some nice drag and drop features so that you can use it and build more complex workflows. But what I want to focus on here is really how we orchestrate executing these, and really what the difficulties were before Temporal and how Temporal was able to solve them. And so at their most basic sense, we did have these graphs. They were different, basically a sequence of logic that we had to run. And the biggest challenge we were trying to solve first was really, we're running arbitrary JavaScript, Python code. We're running random API requests. We need to do this safely, because we're doing this in a multi-tenant environment on cloud. And so at first, we were not worried at all with how can we do this resiliently? How can we handle failures? How can we make sure that we get to the end? We were focused mostly on just running it start to finish. And for that, our architecture was pretty simple. We had a queue of things that had to run. We used Lambda as AWS Lambda as part of our sandboxing strategy, and we used a separate service to kind of run your queries. And so, for example, here, if you were trying to run a Postgres query, we would go through the query runner and query whatever your Postgres database was. This had some benefits. In particular, it's very simple. It's quite easy to scale. But there were some extra features we definitely wanted to add. And there were just a lot of limits that were imposed by this kind of all or nothing execution. Really what we were doing was getting your DAG of logic, sending it to Lambda, and telling it, sort it, run this Postgres query, run this JavaScript block, run all these other things, and if anything fails, the entire thing fails, and you have really no visibility. And so, like I said, this all or nothing execution really was quite painful. Things that were sometimes fading, sometimes weren't, were incredibly hard to track down. We would get ooms in our Lambda function all the time, and we would the best we could do was say, try rerunning it. We'll see if it succeeds the next time. We were also limited to around 15 minutes of execution, which is not great when you're trying to do things like handle flaky APIs. One of the very common use cases we had was, let's say, upload a CSV of 1,000 rows, hit this API that fails half the time or something, and just kind of iterate through it until everything finally succeeds. With Lambda, we really couldn't do that, and we really just couldn't get that resiliency and durability in execution. Another thing we were missing really was just being able to pause. When you're limited to 15 minutes, you can only sleep for so long before your function just gets killed. And it's something we really want to support, especially with companies trying to do business process management, et cetera. You might need to wait for approval from accounting or some other very long-running process, and we just couldn't do that currently. So we kind of went to the drawing board, thought about what could get us to that state. And we needed quite a few things. First of all, we needed something like a state machine. We wanted to know exactly what blocks or activities had been run in our graph. And we wanted to also keep track of every single input and output from each of these blocks. Like I mentioned, a block had access to all the outputs of its parents, and if we ever wanted to add retries, we had to always be able to recreate the state of a specific execution. This was quite a challenge, and we would just need to add we had to add a state machine tracker, some persistence there, retry queues for actually retrying things, and then some way of chaining execution of code to get past that 15-minute limit. And so, while looking at this drawing board and being a bit aware that this is going to be a long undertaking, we started looking at pre-built solutions, and we found out about Temporal. In particular, this Temporal workflow page really resonated with us. This idea of separating your orchestration code from the actual things that were interesting and could potentially fail really fit into our model. You have an actual graph object. The shape of the graph doesn't change. You always want to run the next node in a topographical sort or something. But the actual content of the blocks is what's interesting. You can do SQL statements. You can write whatever Python script you want in there. And also, we thought it might be fun to build a product that was called Retool workflows on Temporal workflows, and then try to explain to everyone that they're not quite the same thing. And so we decided the next step was, let's try to build a proof of concept, really dig deep into, what the platform allowed us to do and where it would fall short for our use case. At this point, we were really just trying to get something at parity with the previous architecture we had. So we didn't want to worry about any of those nice things we wanted. We definitely wanted to support, long sleeps, durable and retry policies. But we decided to omit that in the proof of concept and just build something that works like it did before. And so we decided to kind of use those graphs that we, this kind of graph here that defines a workflow as a DSL on top of Temporal, and a Temporal workflow that just basically translated this DSL into a set of activities with attached retry policies, potentially a set of queries, et cetera. So we're trying to translate the graph we had in the UI to actual Temporal primitives. We first tried the easiest thing we could possibly think of. We have a start trigger that says when we run an execution. And so we said, OK, this is what is actually going to trigger a Temporal workflow to start. And so for crons, we used Temporal cron schedules. And for webhooks, we just had an endpoint in our backend that would call Temporal and start the workflow execution. What got a bit more interesting is how we actually run the graph. For a V0, we again just tried the simplest thing we could, every block is an activity. Each block is arbitrary code. We need to sandbox it somehow. Let's just wrap that in an activity, and we can deploy it wherever we want. In theory, seems like it works pretty good. Unfortunately, like we very quickly knew there was an issue here because each of these blocks is like, arbitrary code. So someone could, for example, do something very reasonable like this. They're trying to like fetch a bunch of 4K images from some API. I guess nowadays you could like call Midjourney to generate a bunch of images. Then you're trying to load them into another internal endpoint. The issue with this is that we made each block an activity. And so as soon as we kind of returned all of that image data, we'd be hit by this very nice blob size limit exceeded error. And we knew this was going to happen. There's this extremely helpful platform limit sheet that Temporal offers. But in particular, because of how Temporal persists everything to an event history, there are pretty strict limits on what gets stored there. And we self-host our own Temporal cluster, so we could play with these a little bit, but there was no way we were going to be able to store 200 megabyte payloads or something in here. That would just be a non-starter for Temporal. And so kind of had to look at everywhere where Temporal, where this error could be thrown or where these arbitrarily large payloads could come in. And there's really only three origin points. There's workflow and activity executions, and there's the SDK client. Again, this was proof of concept, so we went with the simplest solution we could. We kind of just slapped in an S3 or global cloud storage solution in there. As simple solutions usually go, this solved our immediate problem. It introduced a whole bunch of other problems, which is what kind of the rest of the talk is dedicated to. But at least with this, we really were able to really quickly get a proof of concept that worked at parity with our prior architecture, and really start testing what was happening. And so just to dig into the details here, what we would do is get a payload that's 200 megabytes. We would store it in S3, and then in the actual Temporal payload, we would pass in the S3 path to the object. So then every time something else got scheduled, we would just download it from there, which, as this section kind of implies, kind of makes you think about latency just a little bit more. And so kind of to motivate our the importance that we placed on latency, I'm going to kind of run through this example of what our real long-term vision was with kind of migrating to Temporal for this product. Really what we wanted to do was support kind of this paradigm where you have very fast, synchronous pieces of logic that you ran, and then also some very durable, very have to get done pieces of logic. And the idea is that our DSL and graph semantics let you not have to think about what actually has to be run in which mode, and our actual Temporal workflow logic serves as that interpreter. And so we figure out what has to be run quickly, what has to be run slowly, and you don't have to think about that much. So this is a bit of a motivating example. Let's say you're a company accepting payments. You want to set up this webhook where you send it, an account that you want to debit and the amount you want to debit for. There's some logic after where you're authorizing the transaction. And then depending on whether the transaction succeeds or fails, you want to return to the client and actually tell them if the transaction succeeded or failed. You want that to be pretty fast, because if someone's trying to buy something and they're stuck at a spinner for minutes or seconds, it's not a good experience. But then after you authorize this transaction, there's a bunch of cleanup tasks you need to do. You can imagine adding stuff to a bookkeeping system, waiting for some external authorization, or even just waiting for a day and then actually capturing the transaction. And so there was this really interesting overlap where we want the first blue blocks to run very fast, The pie in the sky goal was like almost like an express server, tens of milliseconds of latency. And you want the rest to take as long as it wants. We don't care if this takes minutes, hours, or days, but we need to be sure that there is progress being made. And so there's two problems here. The first is kind of like querying temporal state. And so looking at the example, you want the actual caller of this workflow to know whether it was a success or a failure, but you don't actually finish temporal execution at that point. You kind of want to have a checkpoint in your workflow, return to the caller, and then continue the workflow, which is something we learned recently, that there's like workflow updates which feed this feature, which actually solve this perfectly, but there's still an experimental state, and so we had to come up with another solution in the meantime. And so, and similar to kind of having to inspect that, we had to think about how to use those same blocks to switch between this state where we want this to run as fast as possible. We don't want overhead from using temporal, and then the latter half of this execution where we really do care about all the guarantees that temporal gives us. And so the first question was, how do we solve this querying state? And just reading temporal, like really what the easiest solution would have been using temporal queries. This was a very, very bad solution for our latency case. It's extremely flexible to use temporal queries. You can basically just define a callback. Every time you hit the query, a workflow worker will run through the event history and return the value of the callback. Unfortunately, that's a lot of work, and it is this pull model. And so when you're thinking about synchronous, less than a second or so latency, it's not a great solution. But it is a great solution if you're thinking of querying over days instead of just over seconds. And so, at least for our use case now, this wasn't really the right call. Instead, we had this kind of slightly convoluted two-workflow approach where we made kind of a idempotent workflow execution. It just takes in the graph, takes in scope. We would execute it, and this workflow would actually finish when it hit one of those blocks that we wanted to return a value from. So, for example, here we would start at the trigger. We would go all the way to the successful webhook return. Let's say we get there, and we would return to the client. This was really fast because it was in the request response loop. Really, the only latency we got was from using temporal. But we also had to kind of schedule another child workflow to deal with the leftover expensive post-processing tasks. You can imagine it would probably be quite bad if someone tells us to debit someone $100, we return the 200, and right as we return it, our server dies and we don't schedule the remaining tasks. And so we made it a point to always wait for the child, wait for the workflow that would run the remainder to be accepted by temporal before returning the value. And that kind of solved this problem for us. The latency was pretty small, and we didn't have to think about all of this, these polling semantics. Now, when I say the latency was pretty small, we can think back to the S3 problem I kind of alluded to. In our current very naive approach, each block here is a temporal activity. And what that means is every single block here has an S3 right after it and an S3 read right after you run that one as well. That adds up to quite a bit of latency. And so really, we started testing this, and we saw that even if there was no code inside these, let's say you just had a block that spun up a Python interpreter and returned 5, the latency for this was something near a second, which is not great as the baseline, assuming you're actually going to do work on top of it. And so we had to kind of dig in. We used interceptors to get some more metrics and tracing, and we found out that the biggest issue was that persistence store. So for context, we self-host our own temporal cluster. We use Cassandra as the persistence layer. And we kind of dug in and saw where we were accruing latency. And these are some of the numbers for where we accrued latency for every single activity that we finished or activity that we scheduled. The actual Cassandra there was like super fast. It was under 5 milliseconds for each action. Temporal was also quite fast. The action of like reporting an activity as completed, and then a worker putting the next activity was around 10 milliseconds, which is very negligible. The issue came from our idea to solve the large payload problem. Each put to S3 was around 80 milliseconds, and each get was around 50. And this is for pretty small objects. We were using like order of 10 megabyte objects. If someone was using larger objects, it could be much larger. And if they're using smaller objects, it was unfortunately not much lower. This was like basically the baseline for an S3 request. So every single activity cost us around 140 milliseconds. We don't really want to accrue latency from the programming model we give our customers, and so this is something we definitely didn't want. So we have this very expensive kind of action that we want to decrease the price of, and we really have two options. The first is to have less of them, and the other option is to make them even less expensive. So the first example, the first thing we want to do was make them a bit less expensive. And so this is kind of like a idea of a sample workflow we would have. We really thought about what we were trying to build and realized, for most things, you actually don't need all the durability that Temporal provides. If you're just running some code snippets that never fail, or in particular, like API requests that are not idempotent, you can never retry them. And so there's really not much utility in wrapping this in a Temporal activity with all of the extra cost that accrues. And so kind of came up, expanded our DSL to have a concept of a block that could be retried and a block that couldn't be retried. And so here you can kind of see like the solid line nodes are ones that cannot be retried, and the dashed line nodes are ones that can be retried. We kind of changed our scheduling heuristic, and so all of these blocks we decided to just run the same activity. Whereas other blocks like these that are retriable and need to be run durably, we ran in their own activity, but in parallel. This was a pretty interesting paradigm, just because usually it's very easy to think about parallelization and how things are run when you have a single branch of logic. But if you're in an imperative programming language, trying to come up with this type of algorithm where you can parallelize among multiple branches, especially when each node can take anywhere from a minute to another one taking milliseconds, really was a very big performance gain. There were some use cases we could have written imperatively in code that with this graph paradigm actually ran faster because of this smarter scheduling. And so in this example, we really went from a 16 block or 16 activity workflow, which would have taken around 2 seconds to run, to around 5 activities in parallel, which takes half a second, which is pretty good. We wanted to do a little bit better, so we tried to make each of these also cheaper. Slapping S3 was, not the best idea in hindsight, just adding it there and using it all the time. And so we decided to do a bit more, be more selective with what we store. And so if we had really small payloads, or if we had a DAG that had particularly small blocks, we knew the event history wasn't going to grow much, right? We know each block or each set of blocks in our graph maps to some events in the event history. We can kind of come up with a heuristic that decides what the maximum size of the history will be, and decide when to store to S3 and when to not. Particularly, we also started using our data converters. We were already using them for encryption to make sure that no customer data ended up in Temporal. But we also added on some very fast, like LZ4 compression. This really just took on the order of milliseconds to run, and it sometimes decreased our actual payload size by close to an order of magnitude. And so with these two together, not storing to S3 unless necessary, and then also trying to compress our data before deciding if it needs to be stored in S3, we were able to decrease our latency even more. When we reran the example I went through, we went from over half a second of latency to something like 100 milliseconds. In other more complex workflows, the difference was even more stark. But yeah, that's a bit of like a deep dive into one very specific use case we've worked on. Some of the real key takeaways are like, especially when latency is very important, deserialization and serialization costs are very important to take a look at, and being able to kind of drill those down helps you achieve your latency goals. Likewise, Temporal provides a lot of different constructs like queries, signals, eventually workflow updates. And so really taking like a pretty good survey of them, seeing where the costs and like computation is accrued, helped with like better workflow design decisions overall. But that's a bit of what I had to talk about. I'm happy to move over to Q&A.
Questions? Roberto, I have one maybe to, oh, actually, great.
Hi, thank you for that presentation. You had mentioned earlier, I think, that you were running your workflows as lambdas, and so subject to the 15-minute time limit and those sorts of things.
Yeah.
For your proof of concept, when you were having Temporal be the thing that dispatched the workflow logic, where were you running your workflows in that case? Were you hosting it yourself, or did you find a way to host it in lambdas even with that? Could you talk more about that?
Yeah, that's a great question. So when we first built a proof of concept, we were actually still using Lambda as as part of our sandboxing solution. And so each activity would essentially do separate calls to Lambda. And so each block could be a Lambda function, or a group of blocks could be a Lambda function call. We did eventually decide to move off of Lambda, just because the 15-minute timeout really was not enough, even for like a single block. Sometimes people want to write everything in a single block as a Python script, and we couldn't support that with Lambda. And so we did decide to kind of come up with our own sandboxing solution, and that also, helped cut down on latency, because we were able to better control and like manage the slots in our sandbox service.
Thank you for the talk, by the way. So you mentioned in the talk that when for some API that's not idempotent, you choose to not put them in the activities. Should you further elaborate on that? Because it sounds like in that case, how can you retry, or how can you support replay in that case?
Right. Yeah. Good question. Yeah. So the idea at that point, so I guess all of the blocks that are not idempotent in this case would be the nodes that have a solid outline. And so those will never be retried. And so we kind of don't run them in their own temporal activity. And we make sure that whatever activity they do run in have no retry policies. So that means that it mostly has at most once semantics. If it fails, we fail the entire thing. Yeah.
Hi. So you mentioned that you are self-hosting Temporal. I would like to ask, because when you are onboarding customers to Retool, right, they have different accounts. Are you hosting single Temporal cluster for all your customers? Or is it regionally? Or do you spin up a new Temporal cluster for each customer? And if that's if you're, for example, only using one, how do you upsize the Temporal cluster when you reach the sort of capacity limits with shards or throughput with anything? Yeah, thanks.
Yeah, that's a good question. I think there's a couple parts to it. I think for Retool we have really two offerings. One is like on-premise, customers host their own Retool services, and we actually leverage Temporal Cloud for that. We get a lot of multi-region benefits and are able to spin up namespaces basically on the fly. We do use a self-hosted Temporal cluster for our kind of cloud production instance. So if you don't deploy Retool on your own network, you are using our self-hosted cluster. And there's a few things to managing it. I think the most important, as you said, is like the number of history shards. And there, we really just started off with doing quite a bit of load testing before even spinning up a production server. And we settled on like 4K shards being a pretty good number, where we had space to grow maybe like 10, 50x in capacity before having to add it again. When that time comes, we'll probably have to do a multi-cluster replication and migration and all of that. But I think the fact that we have control over the app level logic and where we call temporal makes that a bit easier because we can always kind of feature flag which cluster it goes to and do that cutover relatively simply. Not super simply, but yeah, we can kind of look inside and see when things are still running and when we can deprecate the old cluster.
I think we have time for one more question if there's any. All right, Roberto, quick question for you. So you're a team and a whole organization relatively new to Temporal. And I would kind of play back your approach here, which is get to an MVP pretty quickly, throw a bunch of stuff at the wall, see how it works, and then kind of iterate from there. Is that a path that you recommend to other teams internally, or any lessons learned from kind of taking the throw it against the wall and see what sticks method?
Yeah, definitely. I think thinking about non-determinism and future changes you might have to make is something you should definitely do at the beginning. I think we definitely had like some time where we kind of just had to rip the Band-Aid off and say, okay, now we have like a new workflow we call it V2, and we have to kind of do a cutover. And that was relatively painful just to avoid any non-determinism errors. I do think there is definitely value in, once you finish thinking about that, kind of just trying to get a proof of concept that doesn't fully leverage temporal, but does kind of just keep parity with your current system. Something we really found was that there were some edge cases we just didn't catch in our V0 until we hit production, and it was just much easier to debug them when we expected the behavior to be exactly the same. Once we were able to establish a baseline and know that the systems were at about parity is when we could actually build out new features and kind of like compare what the executions evolved to.
Cool. Awesome. All right. Well, thank you very much.